Module 7, Lecture B, Cleaning and Scaling. By the end of this lecture, you will be able to identify common data issues such as missing values and inconsistent formats, describe simple strategies for handling missing values and features, and explain why scaling numeric features can help some models behave more sensibly. Common data issues. Handling missing data. Missing data is a common issue in real-world datasets and needs to be identified early for reliable analysis. It occurs when expected values are absent, unknown, or unusable, often due to things like skipped survey questions or sensor failures. In practice, this can appear as empty cells, placeholders such as NA, or clearly incorrect values like negative ages. Being able to recognize both obvious and hidden missing data is essential to prevent it from distorting your results. Missing data can follow different patterns, and recognizing these patterns helps you judge how serious the problem is. Some values may be missing at random, while in other cases, entire variables or time periods are absent, such as a full week of data lost during a system outage. Missingness can also depend on the data itself. For example, when people with high incomes are less likely to report their earnings. When you inspect a dataset, pay attention to where missing values occur, whether they cluster in certain sections, and whether they are related to other characteristics in the data. To detect missing data effectively, you need both technical checks and domain knowledge. Technically, you look for empty fields, special codes, or clearly impossible values, such as a 0 heart rate in fitness data. Domain understanding helps you notice when missing values are hidden, like when a survey uses 0 to mean no response, or when certain groups, such as applicants from specific countries or mature students, lack test scores or GPAs. Treat missing data as an important feature of the dataset that should be carefully identified and documented, not as a minor problem to ignore. Python code, handling missing data. This script demonstrates basic handling of missing data using a very small, simple table. Its main goal is to show how to detect where values are missing and count how many missing entries there are. By focusing on this simple example, it highlights the core idea of identifying and quantifying missing data without extra complexity. We begin by importing the pandas library, which is designed for working with data in tables. Using pandas gives us access to the data frame structure, a powerful way to organize and analyze datasets. This structure is especially useful when dealing with missing values because it includes built-in tools to detect and handle them efficiently. We begin by building a small dataset as a dictionary with 2 entries, age and city. The age entry contains the values 25, a missing value, 40, and -1, where the missing value represents unknown data and -1 represents an invalid age. The city entry contains Paris, an empty string, another missing value, and Berlin, with the empty string and missing value both indicating missing data. This simple dataset is designed to clearly include missing and invalid values that we will later learn how to handle. In Python, a common way to work with tabular data is to use a pandas data frame. We often start with a dictionary where each key is a column name, and each list of values becomes that column's data. When we pass this dictionary into pandas, it constructs a data frame for us. This structure then lets us use pandas' powerful tools for data manipulation, processing, and analysis. This step looks for any age values in the data that are less than 0, which are impossible and therefore invalid. It then replaces those invalid ages with a special missing value marker provided by the pandas library. Using this marker clearly indicates that the data is missing or erroneous. This makes the dataset more accurate and easier to manage and analyze later on. We look for rows in the city column where the value is an empty string and convert those entries into the standard missing value marker provided by pandas. This replaces blank text with a consistent indicator of missing data. Doing this ensures that empty strings are handled the same way as all other missing values in the dataset. We now display the clean dataset to confirm that missing values are properly marked. First, we print a brief message explaining that the table includes missing markers. Then we print the entire data table so we can visually check how the missing entries appear after the cleaning process. To find how many values are missing in each column of a data table, we first use a method that mocks every missing entry with a true or false value in a new table of the same shape. We then sum these true values within each column, which effectively counts how many missing entries that column has. The resulting counts are stored for later inspection and analysis. We begin by printing a short message to introduce the summary of missing values so the listener knows what the upcoming output represents. Then, we show how many values are missing in each column of the data table. This uses the missing value counts we calculated earlier and provides a quick overview of where data is incomplete in the dataset. Together, this message and summary help us quickly identify which columns have missing information. This script shows a simple way to handle missing data in a small dataset. It creates a table with some invalid entries, such as a negative age and an empty city, then converts these into proper missing value markers using a data analysis library. The clean table is displayed with clear indicators where data is missing. Finally, the script counts and prints how many values are missing in each column, giving a quick overview of how complete the dataset is before further analysis. Unit mismatches. In data analysis, a common problem is when the same type of measurement is recorded in different units or with missing unit information, causing a unit mismatch. This can quietly distort results because the data may look consistent even when it is not. For example, patient weights from different hospitals might be recorded in kilograms, pounds, or stones, but all labeled simply as weight. If these are treated as the same unit, patients can appear much heavier or lighter than they really are, and models may learn patterns based on these inconsistencies instead of true real-world relationships. When combining data from different sources, countries, or time periods, it is easy to end up with mismatched units that quietly introduce serious errors. Temperature might be reported in Celsius in one dataset and Fahrenheit in another, or rainfall might be in millimeters in one place and inches in another. Financial data can mix values in thousands of dollars with values in single dollars, and time measurements may combine seconds, milliseconds, hours, and days. These inconsistencies often look normal at first, but can later cause strange model behavior and misleading predictions if they are not detected and corrected. To handle unit mismatches in data, you need to understand the domain and carefully inspect the values. Watch for unusual patterns, such as distributions with separate clusters or values far outside expected ranges, which can signal mixed units like kilograms with grams or kilometers with meters. When you see these issues, check the metadata, talk with data providers, and compare related variables to confirm what each value represents. Then standardize everything to consistent units so your model learns real patterns instead of artifacts from inconsistent measurements. Detecting outliers. When working with a new dataset, it is important to look for outliers, which are values much larger or smaller than the rest. These unusual values may represent rare but real events, or they may be errors such as a misplaced decimal. Because outliers can distort statistical analyses and machine learning models, they can lead to misleading results and unreliable predictions. Detecting and addressing them is therefore essential for accurate data analysis and good model performance. To detect outliers, first use simple descriptive tools to understand the overall shape and spread of your data. Visual methods such as histograms, box plots, and scatter plots help you see where most values cluster and which points stand far away from the rest. For example, in online purchases, most transaction amounts may fall within a typical range, while a few extremely large values could indicate bulk orders or data errors. And an unexpected zero score in a strong class might signal an absence or a recording mistake. Combine these visual checks with summary statistics like the minimum and maximum to quickly flag values that need closer investigation. Detecting outliers is not just about applying algorithms. It also requires judgment and an understanding of the data's context. Values that are rare can still be important, like large financial losses, while others, such as an impossible human height, are likely errors. What looks extreme in one situation may be normal in another, as with different blood pressure settings. With experience, you learn to combine detection methods with knowledge of how the data was collected and what is logically plausible, so you can distinguish meaningful outliers from mere noise or mistakes. Python code detecting outliers. This script demonstrates a simple way to detect numeric outliers in small datasets. It relies on the pandas library for handling the data and matplotlib for creating basic plots. The main goal is to highlight and visualize unusual values so they stand out clearly. By focusing on tiny examples, it keeps the process easy to see and understand. The line that begins with an exclamation mark is a command that installs the Python libraries pandas, matplotlib, and seaborn. It uses a package manager to make sure these tools are available in the programming environment. This setup step is important because it prepares the system for data manipulation, analysis, and visualization. Once installed, the script can use these libraries to work with data and create plots effectively. We begin by importing three key Python libraries: numpy, pandas, and the pyplot module from matplotlib. Numpy handles numerical calculations and random number generation, while pandas offers data structures like data frames for organizing and manipulating data. The pyplot module from matplotlib is used to create plots and graphs. Together, these tools let us manage our data effectively and visualize it to identify patterns and potential outliers. We begin by setting a fixed random seed using the random seed function in the numerical library with the value 42. This makes all randomly generated numbers the same each time the script runs. As a result, the program's behavior becomes reproducible, so we can reliably repeat experiments. This consistency is important for debugging and for verifying that the code works as intended. We simulate purchase behavior by generating a set of amounts that follow a normal distribution. Using a random normal function, we create values with a mean of 50 and a standard deviation of 10, so most purchases cluster around 50 with some variation. We generate 40 such values to represent 40 individual purchases, capturing typical spending patterns with natural noise. We manually create a few extreme purchase amounts to act as outliers in our dataset. Using a numerical array, we specify values like 5, 200, 300, and 400. These amounts are deliberately set far from typical purchase values. This setup lets us test how effectively our outlier detection method can spot these unusual data points. We create one combined dataset of purchase amounts by merging two separate sets of values. The first set represents normal purchases generated to mimic typical buying behavior with some randomness. The second set contains a few extreme amounts that represent unusual or outlier transactions. By joining these two sets into a single array, we obtain a dataset that includes both typical and atypical purchases, which we can later use to detect and visualize outliers. We use pandas to create a data frame that organizes all our purchase amounts in one place. This data frame has a single column called purchase amount, which contains both the normal values and the outliers from our combined data. By storing the data in this structure, we can more easily manipulate and analyze the purchase information using pandas' built-in tools. The code uses a summary function from the pandas library to quickly calculate key statistics for the purchase amounts in the data. It reports values such as the average, standard deviation, minimum, maximum, and quartiles. These statistics give a concise view of how the purchase amounts are distributed and how spread out they are. This overview is useful for spotting unusual values that may be outliers. The code produces a summary of the purchase amounts, showing key statistics such as the minimum, maximum, and quartile values. This summary gives a quick snapshot of how the data is distributed. It helps you quickly spot unusual values and notice basic trends in the purchases without examining every individual data point. To detect outliers using the interquartile range, we start by finding the first quartile, or 25th percentile, which marks the lower edge of the middle half of the data. We then find the third quartile, or 75th percentile, which marks the upper edge of that middle range. Together, these two quartiles define the interquartile range, and values that fall far outside the central portion of the data are considered potential outliers. The code first finds the interquartile range by subtracting the first quartile from the third quartile, which measures how spread out the middle half of the data is. It then computes a lower bound by taking the first quartile minus 1.5 times the interquartile range, and an upper bound by taking the third quartile plus 1.5 times the interquartile range. Any data values below the lower bound or above the upper bound are flagged as potential outliers, since they are considered unusually far from the central portion of the data. We use a Boolean mask to flag rows in the dataset that may be outliers. For each purchase amount, the mask checks whether it is below the lower bound or above the upper bound. If either condition is met, that row is marked as a potential outlier. This makes it easy to filter and focus on values that fall outside the expected range defined by the interquartile range method. In this step, we filter the data frame to keep only the rows where the purchase amount is marked as a potential outlier. We apply an outlier mask, which flags values that fall outside the calculated acceptable range. From these filtered rows, we then extract just the purchase amount column. The result is a series of suspected outlier values that we can examine more closely or include in a report. We first print a short message to explain that we are about to show suspected outliers based on the interquartile range rule. Then, we display the actual purchase amounts that fall outside the calculated lower and upper bounds. These values are identified using the interquartile range method, which flags unusually low or high data points. By listing these values together with their index positions, we clearly show which specific observations are considered unusual in our dataset. To visualize outliers in our data, we first create a new plotting area with a chosen size using a plotting library. We then draw a vertical box plot of the purchase amounts. This box plot summarizes the distribution of the data and clearly highlights any values that fall far outside the typical range. By examining this plot, we can quickly spot unusual purchase amounts that may be outliers. We label the y-axis of the plot to show that it represents purchase amounts in dollars, so listeners understand the scale and units of the data. We then give the plot a clear title, such as box plot highlighting potential purchase outliers, to explain its purpose. Together, the axis label and title make it clear that the visualization is focused on identifying unusually high or low purchase amounts that may be outliers. These elements are essential for helping viewers quickly interpret what the plot is showing. The final step in the script calls the show function from the plotting library to display the box plot. This command actually renders the chart that was prepared earlier. Once the box plot appears, you can visually scan the purchase amounts and quickly spot any values that stand out from the rest. In this way, showing the plot gives you a clear visual indication of potential outliers in the dataset. This script shows a simple way to detect outliers in purchase amount data using Python. It first creates normally distributed purchase values and then adds a few extreme values to act as outliers, combining everything into one dataset. Using pandas, it calculates summary statistics and the interquartile range, then applies the rule that flags values lying more than 1.5 times the interquartile range below the first quartile or above the third quartile. These suspected outliers are printed, and a box plot created with matplotlib visually highlights them, giving a clear picture of the overall distribution and the unusual values. Handling missing data. Removing incomplete data. One simple way to handle missing data is to remove incomplete entries, either by dropping individual records with gaps, or, less commonly, by removing entire features that lack enough values. This approach is attractive because it avoids guessing missing values and keeps the dataset easy to work with. For example, if only a few survey responses are missing an optional question, you might just leave those responses out of the analysis. This quickly cleans the data and reduces the risk of errors from complex imputation. But it is still important to think about why the data is missing and how its removal might affect your results. When deciding whether to remove incomplete data, think about how much is missing and how important the affected features are. If only a few rows are missing values in key variables, it is often reasonable to drop those rows rather than try to estimate the missing values. For instance, in a medical study, you might remove a small number of records that lack a crucial measurement. On the other hand, if a feature is missing from most observations and is not central to your research question, it may be better to remove that feature entirely. This strategy helps simplify the dataset and reduce unnecessary noise in your analysis. Removing rows with missing data may seem straightforward, but it can create serious bias if done without care. When missing values are related to important outcomes or features, deleting those records can distort results, such as overrepresenting more engaged students or losing key financial transactions. This means you might overlook at-risk groups or remove crucial high-value cases. To avoid this, you should study how data is missing, evaluate how much information you lose, and carefully balance having a clean data set against introducing bias and shrinking your sample size. Python code, removing incomplete data. This lesson demonstrates how to safely remove incomplete data using pandas. It focuses on dropping rows that contain missing values in a simple way. As you follow along, pay close attention to which rows are removed so you clearly understand the impact on your dataset. We begin by importing the pandas library, which is designed for working with data in tables. This gives us access to the data frame structure, a convenient way to organize and manage datasets like the one used in this script. By using pandas, we can apply powerful tools for data manipulation. In particular, it provides functions for detecting and handling missing data, which is the main focus of this script. We begin by creating a small dataset that mimics survey results, organized as a dictionary with 3 columns: age, satisfaction, and comment. Each column is stored as a list, and some entries are intentionally left as missing values using none. The age list includes a missing age, the satisfaction list has a missing rating, and the comment list has a missing piece of feedback. This simple example simulates real-world survey data where some responses are incomplete and prepares us to learn how to handle missing data effectively. We begin by creating a data frame with the pandas library, which organizes our information into a table. This is done by passing the existing data dictionary into the data frame constructor. Converting the raw data into this structured format is important because it lets us efficiently manipulate and analyze the survey results. The data frame now contains all the survey data, including any missing values, and is ready for further processing. We start by printing the original dataset, which still contains some missing values. This printout includes a short descriptive message, followed by the full table of data. Viewing the raw data in this way is important because it lets us visually inspect the dataset before cleaning it. By doing this, we can clearly see where the missing values occur and better understand what needs to be fixed. We use a pandas method that checks for missing values to count how many are missing in each column of a data frame. This method creates a mask that marks each missing entry as true. When we then take the sum of these true values for each column, we get the total number of missing entries in that column. This simple step helps us quickly assess how much data is missing before choosing any data cleaning approach. We begin by printing a short message to signal that a summary of missing values for each column is about to be shown, which helps set the context for the next output. Then we display the stored counts of missing values for every column in the data table. This quick overview lets us clearly see where data is incomplete before moving on to any cleaning steps. We use the pandas data frame dropna method to remove rows that contain missing values. By setting the how parameter to any, we tell pandas to drop a row if even one column in that row is missing data. This cleans the dataset by eliminating incomplete rows. As a result, only rows with all values present remain for further analysis. We first show a brief message to indicate that we are about to display the data after removing rows with missing values, so the listener understands the context of the output. Then we present the data frame that remains after dropping any row that contains at least one missing entry. This lets us inspect the clean dataset and confirm that only complete rows are included. Having only fully observed rows is important because it supports more accurate and reliable analysis. To clean the data by removing only rows that lack satisfaction information, we focus on the satisfaction column when dropping missing values. We keep rows where satisfaction has a value and remove rows where it is missing. At the same time, we allow other columns to still have missing data. This targeted approach ensures that all remaining rows are complete with respect to satisfaction, while leaving other parts of the dataset unchanged. We start by showing a brief message to explain that we are about to view data where satisfaction values are always present. Then, we display the data frame after removing any rows that have missing satisfaction entries. This filtering step ensures that every remaining row includes a valid satisfaction value. As a result, we can focus our analysis on complete and reliable data for the satisfaction column. This script shows how to handle missing data in a small dataset using pandas. It starts with a table that has gaps in the age, satisfaction, and comment columns, then prints the original data to reveal those missing values. Next, it counts how many values are missing in each column. The script then removes all rows that contain any missing value and displays the cleaned result. Finally, it demonstrates a more targeted approach by removing only the rows where satisfaction is missing, so you can compare how different strategies affect the dataset. Basic imputation methods. When your dataset has missing values, you do not always need to remove rows or columns. Instead, you can use imputation to fill in the gaps. A simple approach is to replace missing numeric values with a summary statistic, such as the mean or median of the existing data. For example, if some house sizes are missing, you can fill them with the average size from the available records. This keeps the dataset structure intact, allows models that cannot handle missing values to run, and helps preserve the overall distribution of the features. For categorical data, a common way to handle missing values is to replace them with the most frequent category, called the mode. For example, if email is the most common contact method, you would assign email to records where the contact method is missing. This method is simple, keeps the data type consistent, and works well with encoding and machine learning models. However, it can reduce variation in the data and introduce bias if the missing values are not random, so it should be used with care. Imputation methods that use nearby observations are useful for filling in missing values in time series or spatial data. In time series, you can replace gaps with the last known value or the next known value. And in spatial data, you can use values from the nearest location. These approaches rely on the idea that changes over time or space are usually gradual, so nearby observations are reasonable substitutes. However, imputed values are still estimates, so you should consider how they affect model interpretation and uncertainty. Python code, basic imputation methods. This script demonstrates basic methods for filling in missing data, known as imputation. It works with a small housing-style dataset to keep the example simple and clear. The main goal is to show straightforward strategies for handling missing values rather than complex techniques. By focusing on simple approaches, it helps you understand the core ideas behind imputation in an accessible way. We begin by importing the numpy and pandas libraries, which are essential for data work in Python. NumPy supports efficient numerical operations, while pandas offers powerful tools for manipulating and analyzing tabular data. Bringing these libraries into the script prepares the environment for the data processing tasks that follow. We use NumPy's random seed function with the value 42 to make our results reproducible. Setting this seed makes the sequence of random numbers the same every time the code runs. This consistency is important for repeating experiments and for debugging, because it ensures that any randomness in the script behaves predictably across runs. We begin with a small dataset that includes some missing values so we can explore how to handle them. The data is organized as a dictionary with 3 features: property size in square meters, number of bedrooms, and city. Each feature is stored as a list, and some entries in these lists are missing, marked as none. This simple structure provides a clear example for demonstrating different imputation techniques for dealing with missing data in a structured dataset. We first convert the data dictionary into a pandas data frame, which organizes the information into a table with rows and columns. This tabular structure makes the dataset easier to work with for tasks like manipulation and analysis. It also allows us to apply operations, such as imputation, directly to specific columns of the data. We start by showing the original dataset, which still contains missing values, to establish a baseline view before any imputation is done. Pause. A brief message is printed to explain that the data being displayed includes these missing entries. Pause. Then the full data table is printed so we can visually inspect where values are missing and understand the initial state of the dataset. We start by finding the mean of the size in square meters column, which gives the average of all non-missing values. Then, we calculate the median of that column, which is the middle value when the non-missing entries are sorted. These 2 measures summarize the central tendency of the data and will later be used to fill in any missing values in this column. To find the most common city in the dataset, we use a pandas function to compute the mode of the city column, which returns the most frequently occurring city name. We then check whether this result is empty or not. If it is not empty, we take the first value as the most common city and store it. If it is empty, meaning no mode was found, we store a missing value instead. This value can then be used to fill in any missing city entries with the most common city when available. To compare different imputation strategies, we start by making 3 separate copies of the original dataset. Each copy is reserved for a specific method, one for mean imputation, one for median imputation, and one for mode imputation. Working with duplicates allows us to apply each method independently without them interfering with one another. This approach preserves the original data while letting us explore multiple ways to handle missing values. We handle missing values in the size and square meters column by replacing them with the mean of that column, which was calculated earlier. This fills in any gaps in the data using a single consistent estimate. The method assumes that the average size is a reasonable stand-in for the unknown values. By doing this, we keep the dataset complete while roughly preserving its overall distribution. This step updates the size in square meters column in the copied data table by filling in any missing values with the median size that was calculated earlier. This method is called median imputation. It is a common way to handle missing data because using the median reduces the influence of extreme values compared to using the mean. To handle missing values in the city column, we first check that the column has a valid mode, meaning a most frequently occurring value. If this mode exists, we use it to fill in all missing entries in the city column of the copied dataset. This replaces missing values with the most common category, which is a standard method for imputing missing categorical data. We start by making a copy of the original data table so the initial values are preserved. On this copy, we apply forward filling to the bedrooms column. Forward filling replaces each missing value with the most recent non-missing value that appears above it. This method is especially useful for data with a time-like order because it maintains continuity by carrying the last known value forward to fill gaps. We first print a short message to indicate that we are about to show the results of mean imputation for the size column. Then we display the values in that column after the missing entries have been filled with the mean. This allows us to directly observe how the imputation changed the data and to clearly see the effect of using the mean as the filling strategy. We first print a short message to explain that we are about to show the values of the size in square meters after median imputation. Then we display that column from the dataset, where all missing entries have been replaced with the median of the original size values. This output lets the user see exactly how the missing data has been filled in using a central tendency measure and understand the effect of the median imputation step. We first print a short message to signal that we are about to show the city column after mode imputation. Then we take the city column from the data table where missing city entries have been filled in using the most frequently occurring city name. Finally, we display this updated column so we can see how the previously missing values have been replaced by the mode. We now show the bedrooms column after applying forward fill to handle missing values. Forward fill replaces each missing entry with the most recent non-missing value that appeared above it in the data. This method is especially useful for time-like data, where using the previous value is a reasonable estimate for a missing one. Displaying this column helps make clear how the forward fill imputation has been applied. This script shows how to handle missing data in a small dataset using simple imputation methods. It first creates a table with gaps in the size, bedrooms, and city columns, then calculates the mean and median for size and the most frequent value or mode for city. Copies of the data are used to compare different strategies. One fills missing size values with the mean, another with the median, and missing city values are filled with the mode. For the bedrooms column, it uses forward fill, carrying the last known value down to the next missing entry. Finally, the script prints the original data alongside each imputed version to illustrate how these methods change the dataset. Recording data assumptions. When you handle missing data, you are not just performing a technical step. You are making assumptions about the real world your data represents. For example, filling in missing ages with an average assumes those people are similar to others, and dropping rows with missing income assumes the remaining data still represents your target population. It is important to write down these assumptions along with your data preparation steps. This documentation supports transparency, makes your work reproducible, and allows others to review or revise the assumptions later. When working with missing data, it is important to record why you chose each way of handling it. For example, if you fill missing temperature values with the last recorded value, you are assuming the temperature stayed stable during that time. If you treat missing last login dates as if the user never logged in, you are making a strong assumption that must be clearly stated. By documenting these choices in a project log or data dictionary, you create a transparent path from the original data to your final conclusions. When handling missing data, you need to be clear about the uncertainty and possible bias your choices can introduce. Simple fixes, like filling in missing exam scores with the class average, dropping incomplete health records, or treating missing purchase amounts as zero, can distort variability, exclude important groups, or underestimate revenue. By recognizing these limitations from the start, you can better judge how robust your models are and adjust your approach as new information appears. This careful reflection supports more ethical, reliable data analysis and helps ensure your pre-processing decisions accurately represent the story your data is telling. Why scale features? Uneven feature scales. Uneven feature scales occur when numeric variables in a dataset have very different ranges because they use different units of measurement. For example, in housing data, house size, price, and number of bedrooms can be on very different scales, with price possibly in the millions and bedrooms in single digits. While humans can easily interpret these differences, many algorithms only see the raw magnitudes of the numbers. As a result, features with larger numerical values can dominate the learning process and distort what the model pays attention to. When features in a dataset have very different scales, models that rely on distances or gradients can behave poorly because they implicitly treat all features as equally important. A feature with large numeric values can dominate learning, even if it is not more informative than others. For example, in housing data, large price values might overshadow features like the number of bedrooms, and in medical data, a small range genetic risk score might be ignored compared to larger scale measurements. Without proper scaling, these imbalances can distort what the model learns and lead to misleading results. When features in a dataset use very different scales, it can make models harder to interpret and debug because the raw coefficients or parameters become misleading. In linear models, a feature measured in large units may get a small coefficient compared with a feature measured in small units, even if they are equally predictive, which can confuse judgments about importance. In clustering or nearest neighbor methods, large-scale features such as income can dominate smaller but important features and distort how similarity is measured. As a result, decisions like marketing offers or patient follow-ups may end up reflecting measurement artifacts instead of true patterns in the data. Python code uneven feature scales. This script demonstrates how uneven feature scales can affect analysis of housing data. It compares raw numeric house features with their scaled versions to highlight the difference. The key idea is that features with much larger numeric ranges can dominate distance calculations. By examining both raw and scaled features, you can clearly see how large scales overshadow smaller ones when measuring distances. We begin by importing two key Python libraries to prepare for data analysis. NumPy provides efficient tools for working with arrays and performing numerical calculations. Matplotlib's plotting module allows us to create visualizations so we can display and compare data features. Together, these imports give us the basic tools needed for data manipulation and visualization in our script. We set a deterministic random seed using the numpy random seed function with the value 42, so that any random numbers generated are the same each time the code runs. This makes the script's behavior repeatable and ensures that results do not change between runs. Such reproducibility is important for reliable debugging and testing because it allows us to consistently reproduce and analyze the same outcomes. We begin by building a small synthetic dataset that represents house features, focusing only on house size. Using a numerical array of floating point values, we specify the sizes of 5 different houses. These sizes are chosen to span different magnitudes, so that later we can clearly show how uneven feature scales can affect distance calculations in our analysis. We create a numpy array to store house prices as floating point numbers. These price values are much larger in magnitude than other features, such as size or number of bedrooms. This difference in scale is intentional because it shows how features with larger numeric values can dominate calculations like distance measurements if the data is not properly scaled. We represent the number of bedrooms in each house as an array of floating point values: 2, 2, 3, 4, and 5. Using floating point numbers here is consistent with how other features are stored in the dataset. This example also shows that bedroom counts have relatively small values compared with other features, like prices, which emphasizes that the dataset contains features on very different numerical scales. We combine the size, price, and bedroom arrays into one matrix using a column stacking operation, where each array becomes a separate column. This creates a two-dimensional dataset in which each row corresponds to a single house and each column represents one of its features. Having all features in this unified format is important for later steps, such as computing distances or applying scaling. This approach also implicitly checks that all arrays have the same length, which helps maintain consistent and reliable data across features. The code prints the shape of the feature matrix to quickly verify that it has the expected number of rows and columns. This simple check confirms that the data is organized correctly before moving on. Ensuring the matrix structure is correct is important because later operations depend on this arrangement. If the shape is wrong, it signals that something went wrong earlier in the data preparation process. We begin by choosing a reference house to use in our distance calculations. Here we set the reference index to 0, so the first house in the dataset becomes our baseline. All other houses are then compared to this one to measure how far they are from it. This applies to both the original feature values and their scaled versions, giving us a consistent point of comparison throughout the analysis. To find the raw Euclidean distance from a reference house to each other house, we compare their features. For every house, we subtract the reference house's feature values from its own to get a set of differences. We then square these differences, add them up across all features for that house, and take the square root of this total. The result is a Euclidean distance that tells us how far each house is from the reference house in terms of their original feature values. We first print a short message to signal that we are about to show the raw distances from the first house, so the listener understands the context of the numbers that follow. Then we display these previously computed distances, rounding them to 2 decimal places to make them easier to read and interpret. Seeing these values helps reveal that the price feature, because it has a much larger scale than the others, dominates the distance calculations. This highlights how uneven feature scales can strongly influence distance-based methods. To standardize the housing data, we first compute the mean of each feature across all houses, giving the average value for every feature. We then calculate the standard deviation of each feature, which measures how much the values vary around their mean. Using these 2 quantities, we can scale the features so they have 0 mean and unit variance. This standardization ensures that all features are on a comparable scale and that no single feature dominates when we compute distances. When standardizing features, we must avoid dividing by 0. To do this, we use a function from numpy that checks whether any standard deviation values are 0 and replaces those zeros with 1s. This guarantees a safe denominator during scaling and prevents computational errors caused by division by 0. As a result, the standardization process remains stable and reliable. We standardize the feature matrix by first subtracting the mean of each feature from its values, which centers them around 0. Then, we divide these centered values by the standard deviation of each feature, so that they all have unit variance. This transformation puts all features on a comparable scale. As a result, each feature contributes equally to distance calculations, and no single feature dominates, simply because it has larger numerical values. To find the scaled distance from each house to a reference house, we first subtract the reference house's scaled feature values from the scaled features of each other house. This produces a set of differences for every house. We then compute the Euclidean distance by squaring these differences, summing them for each house, and taking the square root. The result is a single distance value for each house, where all features contribute on a comparable scale because they were standardized beforehand. We calculate and display the scaled distances from the first house to all other houses to show that, after scaling, each feature contributes on a similar level to the distance calculation. To make these values easier to interpret, we apply a rounding step that keeps only 2 decimal places. This helps us clearly see and compare the effects of scaling on the distance measurements. To prepare our plot, we first create positions along the x-axis that match the number of houses in the dataset. Using a numerical array of indices, we assign each house a unique x-axis location. This lets us place both the raw distances and the scaled distances at the correct positions, so we can visually compare them for every house in the data. We create a bar plot to compare raw and scaled distances in a clear, readable way. The figure size is set to 6 by 4 inches to keep the visualization easy to interpret. A bar chart is then drawn for the raw distances, with the bars slightly shifted to the left of each index, so there is space to add the scaled distances later. Each bar has a fixed width, and a label is included so the raw distances are clearly identified in the legend. Next, we add bars that represent the scaled distances to the bar chart. We shift these bars slightly to the right of the raw distance bars so they appear side by side for easy comparison. The scaled distance bars use the same width as the raw distance bars, and we label them as scaled distances so they are clearly identified in the legend. We create a bar plot where the x-axis shows the house index. So each bar corresponds to a different house, and the y-axis shows the distance from the first house, so the bar height represents how far each house is from that reference. The plot title, Effect of Uneven Feature Scales on Distances, emphasizes that we are comparing how using raw features versus scaled features changes the distance calculations. A legend is included to clearly distinguish the bars for raw distances from those for scaled distances, making the comparison easier to interpret. The script ends by calling the plotting library's show function to display a graph that compares distances between houses before and after feature scaling. This visual comparison makes it easy to see how scaling changes the relative distances. By looking at the plot, we can clearly observe the effect of uneven feature scales on distance calculations and understand why scaling is important. This script shows how unequal feature scales can distort distance calculations in a dataset of house characteristics. It first computes Euclidean distances using raw values for size, price, and number of bedrooms, and reveals that price dominates because it has the largest numeric scale. Then it standardizes all features to have zero mean and unit variance, and recalculates the distances so each feature contributes more equally. A bar chart compares distances before and after scaling, emphasizing why feature scaling is crucial for distance-based analyses. Model sensitivity to scale. Some machine learning models are very sensitive to the scale of numeric features, so large numbers can dominate learning even when they are not more important. For example, when predicting house prices, square meters may overshadow the number of bathrooms simply because its values span a larger range. This is especially problematic for models that rely on distance calculations, where large-scale features stretch the feature space and make smaller-scale features contribute very little. As a result, differences in scale can distort the model's understanding of which features truly matter. Many machine learning algorithms are sensitive to the scale of their input features. In gradient-based methods like linear and logistic regression, features with much larger values can dominate the optimization, slowing convergence and making the process unstable, while smaller-scale features are underused. In distance-based methods, such as k-nearest neighbors and clustering, features with larger numeric ranges can overwhelm distance calculations, making them seem more important than they really are. Proper feature scaling helps ensure that all features contribute fairly to learning and decision-making. When using models with regularization, the scale of the input features strongly affects how we interpret their coefficients. Regularization penalizes large coefficients, so if features are on very different numeric scales, the model may unfairly shrink some coefficients more than others. A feature measured on a small scale might need a large coefficient, while a feature on a large scale might need only a small one, and the penalty can distort this relationship. By scaling features to similar ranges before training, the model can assign coefficients that better reflect each feature's true predictive importance, rather than differences in how they were measured. Python code. Model sensitivity to scale. This script demonstrates why feature scaling is important in machine learning. It compares distances between data points before and after scaling the features. The key idea is that one feature with much larger values can dominate the distance calculations. After scaling, all features contribute more fairly to the distances. This script is designed to run in Colab, a cloud-based Python environment where the needed libraries are already available, so you usually do not need to install them yourself. It mentions that if the numpy library is ever missing, there is a commented instruction showing how to install it with a package manager. This setup helps ensure that all required dependencies are present so the script can run smoothly. We begin by importing the numpy library, which is a key tool in Python for fast numerical work. NumPy lets us create and manage arrays efficiently and perform many kinds of mathematical and statistical calculations. In this script, it will be used for tasks such as building arrays, computing statistics, scaling values, and measuring distances. By importing NumPy at the start, we make these capabilities available throughout the code. We begin by setting the random seed in the numerical library to the value 42, so that any random numbers generated will be the same every time the code runs. This makes the results reproducible, which is important for debugging and for verifying that the code behaves as expected. By fixing the seed, we can consistently repeat experiments and compare outcomes with confidence. We create a small dataset with 2 numeric features to show why feature scaling matters in machine learning. One feature contains small values from 1 to 4, while the other contains much larger values from 1,000 to 4,000. Because the second feature is so large, it can dominate distance calculations between data points. This example highlights that without scaling, large features can overwhelm smaller ones and distort distance-based methods. We start by combining the 2 features, the small one and the large one, into a single matrix using a column stacking operation, so that each observation becomes a row and each feature becomes a column. This creates a 2-dimensional array that organizes the data for further analysis. After stacking, we check the shape of the matrix with an assertion to confirm it has 4 rows and 2 columns. This verification step ensures the data is structured correctly before moving on. We choose a reference point that closely matches the first row of our dataset, represented as a 2-element array with values 1.5 and 1500. This ensures the reference point has the same number of features as the data, which is necessary for computing distances correctly. We then verify that its shape is exactly 2 elements, confirming it is consistent with the feature dimensions of the dataset. This function computes the Euclidean distance between 2 points represented as arrays. It does this by finding the difference between each pair of corresponding elements, squaring these differences, and adding them together. Then it takes the square root of this total to produce the distance as a floating point number. This measure tells us how far apart 2 points are in a multidimensional space and is important for understanding how feature scaling affects distance calculations. We begin by creating an empty list to store distances before any scaling is applied. For each row in the dataset, which includes both small and large features, we compute its Euclidean distance to a fixed reference point using a function that subtracts the points, squares and sums the differences, then takes the square root. We add each resulting distance to the list. This process lets us see how the large feature has a much stronger influence on the distance values before scaling is used to balance the features. To standardize a dataset, we first compute the mean of each feature across all samples, which gives the average value for every feature. We then calculate the standard deviation of each feature, which tells us how much the values vary around that mean. Using these 2 statistics, we can transform each feature so that it has a mean of 0 and a standard deviation of 1. This standardization step is important for many machine learning methods that assume features are on a comparable scale. When standardizing features, we must avoid dividing by 0 if a feature has 0 standard deviation. To handle this, we use a function from the numerical library that checks each standard deviation value. If a value is 0, it is replaced with 1. Otherwise, it is left unchanged. This simple adjustment prevents division by 0 errors when scaling the data. We scale both the dataset and the reference point using their means and standard deviations so they are treated consistently. For each feature, we subtract its mean to center the values around 0, then divide by its standard deviation, so the spread becomes 1. We apply the same transformation to the reference point. This standardization is important because it prevents features with larger numerical ranges from dominating distance calculations. We first confirm that the scaled dataset has the same shape as the original dataset, which tells us that scaling has not changed the structure of the data. We then check that the scaled reference point also matches the shape of the original reference point. These checks verify that scaling was applied correctly and that the data's integrity is preserved. Only after this validation do we move on to computing distances. After scaling the features, we recalculate the distances to see how scaling changes them. We create an empty list to store these new distances. Then, for each row in the scaled dataset, we compute the Euclidean distance between that row and the scaled reference point. Each distance is added to the list, giving us a full set of scaled distances. Comparing these values with the original distances shows the impact of feature scaling on distance calculations. We first print a header that labels the output columns as index, raw distance, and scaled distance, so it is clear what each value represents. Then, we loop through the pairs of raw and scaled distances and print each index with its corresponding values. The distances are rounded to 2 decimal places to keep the output easy to read. This side-by-side display lets us clearly see how scaling changes the distances and how feature scaling can affect the model's sensitivity. This explanation emphasizes why feature scaling is important in machine learning models. Scaling keeps different features on a similar range so that none of them dominates the distance calculations just because it has larger numeric values. Without scaling, features with bigger numbers can overpower others and distort the model's behavior. By ensuring each feature contributes more equally to the distance metric, scaling supports more accurate and reliable predictions. This script shows why feature scaling is important in machine learning by comparing Euclidean distances before and after scaling. It uses a small dataset with one feature on a small scale and another on a much larger scale, and demonstrates that without scaling, the large feature dominates the distance calculations while the small feature has little effect. The script then standardizes both features using their means and standard deviations, taking care to avoid division by zero. After scaling, the recalculated distances show that both features now contribute more equally, highlighting that scaling is crucial for models that are sensitive to the scale of input features. Normalization basics. Data normalization is the process of adjusting numeric features so they share a common scale, such as mapping values into a range from 0 to 1. This transformation keeps the relationships in the data the same, while making it easier for models to compare and combine different features. By putting all measurements on a similar scale, no single feature dominates just because it uses larger units. For example, in customer behavior analysis, normalization helps annual income and website visit duration contribute more equally to the model's results. Normalization is a way to put different kinds of measurements, like time, distance, and scores, onto a common scale so they can be compared fairly. It changes the magnitudes of the values but keeps their order the same, so better performances or higher values still rank correctly. This helps models interpret mixed data types, such as age, income, and satisfaction ratings, in a consistent and meaningful way. Normalization is important because it stabilizes and speeds up the training of models. When features have very different scales, optimization becomes unpredictable, and small changes can affect some features much more than others. By putting features on a similar scale, the model reacts more uniformly to updates, which leads to faster convergence and more reliable results. This consistent behavior is especially critical in areas like credit scoring and medical prediction, where effective learning can strongly influence outcomes. Python code, normalization basics. This script introduces the basic idea of feature normalization in data processing. It compares raw numeric features with their normalized versions to show how scaling changes their ranges. The focus is on two common methods: min-max normalization, which rescales values to a fixed range, and z-score normalization, which centers data and adjusts it based on standard deviation. Together, these examples highlight why and how numeric features are normalized before further analysis or modeling. This script runs using only the standard Python libraries, so you do not need to install anything extra. Because everything it needs is already included with Python, you can execute the code right away. This makes it easy to try out the script and focus on understanding and experimenting with feature normalization. We begin by importing the numerical computing library numpy, which is designed for efficient work with arrays and mathematical operations. This step is necessary because the script relies on numpy to handle data manipulation. It also uses numpy's tools to perform normalization and other numerical tasks that follow in the code. We begin by creating a small dataset using a numerical array with 4 rows where each row is a data point containing 2 features: age and income. Age values are relatively small, while income values are much larger, so the 2 features are on very different scales. This contrast in scale is intentional because it helps illustrate how normalization methods can adjust these values so that age and income become more comparable for analysis. We begin by printing the raw data so we can see the original scales of the features. This lets us understand the range and distribution of the values before any normalization is done. By first examining the unscaled data, we can later compare it to the normalized versions and clearly see how scaling changes the data. To prepare data for normalization, we first compute the minimum value in each column of the dataset, treating each column as a separate feature. We then compute the maximum value for each column in the same way. These minimum and maximum values define the range of each feature. Knowing this range is essential because it provides the bounds we use to scale or normalize the data. Min-max normalization rescales each column of a dataset so that all feature values fall between 0 and 1. To do this, we subtract the minimum value of each column from every entry in that column, shifting the smallest value to 0. Then we divide by the range of that column, which is the maximum minus the minimum, so the largest value becomes 1. The result is a normalized dataset, where all features share a common scale, making them easier to compare and analyze. The code prints the data after applying min-max normalization. This is important because it lets you compare the original values with their normalized versions. By viewing the normalized data, you can confirm that all features have been rescaled to a common range, usually between 0 and 1. This makes it easier to see how normalization changes the data distribution and prepares it for further analysis or machine learning. To prepare raw data for machine learning, we first compute the mean of each column, giving the average value of every feature across all data points. We then compute the standard deviation of each column, which tells us how much the feature values vary around their mean. These two statistics are used to standardize the data so that all features are on a comparable scale and contribute more equally to the analysis. To keep normalization numerically stable, we avoid dividing by 0 by first checking the standard deviation values. If any standard deviation is 0, we replace it with 1. This way, when we divide by the standard deviation during normalization, we do not trigger division by 0 errors. This simple conditional replacement step is essential for a robust normalization process. Z-score normalization is a way to standardize a dataset by centering and scaling its features. For each column, we subtract the mean from every value to center the data around 0. Then, we divide these centered values by the column's standard deviation to adjust for variability. After this transformation, each feature has a mean of 0 and a standard deviation of 1, which makes features with different original scales easier to compare. We print the z-score normalized data alongside the raw data so we can directly compare them. This shows how normalization changes the original feature scales by shifting the values to be centered around 0. It also scales the data based on the standard deviation. Seeing this comparison helps us understand how normalization affects the overall distribution of the dataset. We begin by selecting the first data point from the raw dataset, which represents one individual's features, and then selecting the fourth data point from the same dataset. These 2 points will later be used to compute the Euclidean distance between them. By comparing this distance before and after normalization, we can see how scaling the data changes the measured distance between points. We use Euclidean distance to measure how far apart 2 points are in the original dataset. To do this, we rely on a linear algebra tool from the numerical computing library to compute the norm, which gives the straight line distance between point A and point B. This calculation tells us how separated the 2 data points are in their original feature space. We compute the Euclidean distance between 2 points in the min-max normalized dataset by taking the first and last rows, which represent 2 different data points, and measuring how far apart they are. To do this, we use a linear algebra norm function from a numerical library to calculate the distance between these 2 normalized vectors. This calculation shows how min-max normalization changes the scale of distances between data points while preserving their relative differences. We first compute the Euclidean distance between 2 points using the original data to see how far apart they are without any scaling. Then we compute the Euclidean distance between the same 2 points after applying min-max normalization. Comparing these 2 distances shows how normalization changes the scale of the data, and therefore changes the distances between data points. This script shows how basic feature normalization works, using a small dataset with age and income. It first prints the raw data to highlight that these features are on very different scales. It then applies min-max scaling, which maps values to a range between 0 and 1, and z-score normalization, which centers values around 0 with a standard deviation of 1. The script prints the normalized results so you can compare how the scales change. Finally, it computes the Euclidean distance between 2 data points before and after min-max normalization, demonstrating that distances shrink after scaling and that normalization changes the geometry of the feature space. In this lecture, you learn to identify common data issues such as missing values and inconsistent formats, describe simple strategies for handling missing values in features, and explain why scaling numeric features can help some models behave more sensibly. In the next module, Module 8, we will go over nonlinear models. Thank you for your attention. See you all in the next lecture.